Okay, we're back, and I'll try to pick up the pace a little bit so I can get through this. This is the odd nomenclature from your worksheet, and hopefully you were able to follow the last one. I'm going pretty quickly, but you have heard this before, and you can rewind. So things started getting a little sloppy. I'm going to finish this slide here up, and then I have three more after it, and the three after it I'm going to focus mainly on the odd nomenclature, but I will throw an even in every now and then. So we've done a lot of these. I'm going to be going now to iron bicarbonate, which is an ionic compound, and it starts with iron. That's a metal. I see that Roman numeral there, and I know immediately that I have a 2 plus for the charge on the iron ion. Iron can also have other charges, so we have to make sure that we pay attention to that Roman numeral. Bicarbonate, you added this to your polyatomic ion reference sheet. It's HCO3 negative. We will need two bicarbonates at a total of -2 to balance out this +2 charge. So when I write the formula here, I'm going to have one iron, and then in parentheses, I'm going to have two bicarbonate ions. So I'm going to put the bicarbonate in parentheses and put a 2 on the outside. I have to make sure that I put the polyatomic ion in parentheses if I have more than one. And since I have 2, I put a 2 subscript on the outside. We did acetic acid, hydroiodic acid. Now we're on ammonium oxide. I know that this is ionic because it starts with ammonium, so you got to be able to recognize this guy. He's very common. So the ammonium ion is spelled AMMON. IUM. Look on your chart. You should know how to spell this. Now, our anion is monatomic. There's only one element here, so I just look at my periodic table, and I know that this is oxygen, of course, and so it ends in IDE since it's a monatomic anion. Here we have tartaric acid. Here we have dinitrogen trioxide, hexane, and now we have another ionic compound. Our metal is sodium. Now, unlike the guy next door, sodium does not get a Roman numeral. Sodium only has one charge. It'll lose one electron, so we don't need to put a Roman numeral. So remember what that rule is. Groups 1 and 2, the metals never get a Roman numeral. The sliding board elements, aluminum, zinc, cadmium, and silver, never get a Roman numeral. All other metals on the periodic table need to be shown with a Roman numeral when they're named. So we have sodium, no Roman numeral, and then we have hydroxide. You have to use your polyatomic ion chart in order to figure this out. So, on to the next slide. This is a little bit fuzzy. I apologize. It's the best I could do with my camera scanner. So we are on sulfur hexafluoride. I'm going to do the odds here. I look at this and I wonder what the heck this is. And I think about it, I've got two nonmetals, so sulfur, fluorine, on the right side of the periodic table to the right of the stair-step line. There's nothing in front of sulfur, so I only have one sulfur. Now, fluorine, I've got 6. Hexa means 6 fluoride. Now don't make the mistake of putting the 6 here, because that's going to tell you have 6 sulfur. So you write the formula for the fluorine, and then you're going to put the 6 afterwards. Sulfur hexafluoride. Down to here, chlorine dioxide. Again, we have a binary covalent compound, just like we had up here, a binary covalent compound. We don't see anything in front of here. We never put a mono there, so it's going to be 1 chlorine, and then, of course, 2 oxygen. But we're going to put O2 instead when we write the formula. If you get confused about these, just think about, going up here, just think about carbon monoxide. Just think about carbon dioxide. These are so common and you've seen them before. Just think about what the names are for these and follow that pattern. Magnesium iodide, ionic, and I can tell because magnesium's a metal. Since this ends in IDE, the iodide monatomic. Don't mistake it for iodate or iodite. So magnesium, the charge is going to be 2 plus because it's in group 2. Always loses 2 electrons when it forms an ion. The iodide, I1 minus. So you can see right here that what's going to happen is I need 2 iodides for every 1 magnesium. So my formula is MgI, and I have a hat and I have shoes on my I2. We don't want it to look like an L. Calcium phosphite. Now, another ionic compound. Calcium is a metal, and its symbol is Ca2+. It's in the same group as magnesium, charge of 2+. Now phosphite, be careful. Not on your table, but if you know phosphate with a symbol of PO4 3-, and you take off an oxygen, here you have PO3 2-, or excuse me, 3-, whoops. All right, so on calcium phosphite, when we look at this is a little bit harder for people. You have to have charges that add up to 0. Well, if you add another calcium in, that's going to be a charge of 4+ and 3-. And if you add another phosphite in, it'll be 4+ and 6-. So you'll need 3 calciums and 2 phosphites. An easier way to think about that is to multiply the 2 and the 3 together. And don't worry about the negative right now, but multiply these together. Your lowest common multiple is 6. So that means you're going to have a positive 6 charge and you're going to have a negative 6 charge total. 6 divided by 2 is 3. 6 divided by 3 is 2. So what that tells you then is you're going to have 3 calcium ions for every 2 phosphite ions. Up here, this guy right here, we got to break it down. This element here is mercury. This is an ionic compound. Mercury is going to be a metal. So we have to do here, since there's more than one type of mercury, is we have to break it down and we have to look at what the charge on the oxide is. Remember, there's mercury 1. That's kind of funny. That's polyatomic. And mercury 1 is written Hg2 with a 2+ charge. And it's called mercury 1 because we have a mercury Hg1+ that's bonded together with another Hg1+. And so we have 2 of them, and the total charge is 2+. So we don't know if it's that one or if it's this guy, Hg2+. We have to kind of figure it out. Now, if we look at this, we will be able to figure it out, because if it's mercury 2 and oxide is a charge of 2-, our formula would not be Hg2O, it would be HgO. So that's our indication that we have something here that's mercury 1. Now another way I could do that is I could assign this a charge of 2-. I could assign this a charge of 2+. And what that would tell me is that the charges would even out, so I'd have 1 of each, but that's not my formula. So I have to write this very carefully. I indeed have the mercury 1 ion, and this is tricky. So I've got mercury 1, you can put this in parentheses if you want, oxide. Mercury 1 oxide. There we go. This guy here is a hydrocarbon. As you can see, this is a hydrocarbon. Remember, it's carbon then hydrogen. We have a ratio that's not 1 to 2, but it's 1 to 2 plus 2. That means I have a chain. If I have a chain, I do not put cyclo in front of it because it's not a ring. And so I just look and see how many carbons I have. I've got 9. I remember the prefix, and I put A, N, E at the end. Down here, I have oxalate. I have to recognize that oxalate. It starts with hydrogen, so I know I have a ternary acid named from the oxalate ion. Well, if this is oxalate, then my acid is going to go from 8 to ick. Remember, ick, I ate it, when you get that bug in your throat. So this is oxalic acid. Down here, zinc. Oh, a metal. IC. Zinc is on the sliding board, no Roman numeral needed. So we have zinc with a C, of course. And then this guy right here is not chlorate, it's perchlorate. And you got to know those ions, folks. If you don't know those ions, oh boy, is your life going to be rough for the rest of the year. Now, I'm going to move on to the next side of the sheet here. I'm going to go through these pretty quickly, so pay attention. Hydro, binary acid, ick. All right, so I've got a binary acid, hydrogen, and I've got bromide. So this is going to be HBr. Hydrogen is 1+, bromide 1-. It's a halogen, 1 of each. Does add up to 0. Hypochlorous acid. Now don't be fooled. Hypo is not the same as hydro. Hypo is simply a prefix that goes with the polyatomic ion, and it will always be with an us ending. So this means if I have a hypo-us acid, I have a hypo ite ion that this is from. So I have to think what my hypochlorite ion is, and it's going to be ClO negative. So if I've got hydrogens, since I only have a -1 charge for my anion, that means I'm only going to have one hydrogen present. So this is going to be HClO, AQ of course, and AQ up here. Methane, monkeys eat peanut butter, it ends in ANE. This is a hydrocarbon. It doesn't say cyclo, and it couldn't be cyclo anyway because you can't have more than one carbon, or excuse me, one carbon cannot hold hands with anything else if there's just one there. So we have a chain hydrocarbon, and what we do is meth stands for 1. We put one carbon in. 1 times 2 is 2, plus 2 is 4. So the formula for methane is CH4, and it looks like this. Remember, carbons have 4 bonding sites, and so this carbon is going to have a hat hydrogen, a shoe hydrogen, and 2 mittens on the end. If we go down to cesium oxalate, cesium, this is a metal. Cesium, geez, I forget, cesium, francium. I think it has a charge of 1+, and if it doesn't, I'm sorry, I'm doing this off the top of my head because I don't have my periodic table with me. Oxalate, C2O4, 2-. 2 wheels on the ox cart, 2 wheels on the cart, 4 legs on the ox, 2 legs on the farmer who's the mean guy because he's whipping this dude. So we have 1+, I hope, and we have 2-. If this is the case, then my formula is going to show that I have to have 2 cesiums for every single oxalate. And if this is not right, then cesium is actually a group 2 metal, and we'd have one of these and one of these. And I will look at that shortly, but I don't have a periodic table in front of me. If you go up to 47 over here, 47 shows us an acid, and we know it's an acid because it starts with hydrogen. So if it starts with hydrogen, whoops, if it starts with hydrogen, got to be an acid. All right, so here we are right here. I have a ternary acid because it has oxygen in it. So this is a ternary acid. I have to identify this ion. It's nitrate. So remember, I ate it. If that was the nitrate ion, it's going to be nitric acid. Down here, I have a metal and I have a nonmetal. This is an ionic compound. Silver, it's on the sliding board. It does not need a Roman numeral. So I've got silver fluoride, FLUO, pet peeve, IDE. Chromium and oxygen. Chromium is a metal. Now, chromium is in the transition metal or the D block, and it will have to have a Roman numeral. We work off of the anion when we have to figure that out. So this is an ionic compound because it contains a metal. Now, be very careful here because you probably get used to just looking over here and pulling this subscript out and then putting a Roman numeral there. So you'd think it would be chromium 3 oxide. It's not. You have to be careful. Oxide's always 2-. If you have 3 of them, that's a total negative charge of 6-. And if you have 1 chromium, then it's got to have a charge of 6+. All right, so positive 6 and negative 6 equals 0. So this actually is chromium 6. That's a UM. VI is 6, and it's oxide. Oxide's monatomic. Now, right here, this is a little tricky. This isn't a compound. I threw it in. I don't know why. This is actually just diatomic iodine. And I think I have a choice on the front that you can call this a diatomic molecule since it occurs in 2s. Remember our diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, H7, H-nofkelbrei, Hofbrinkel, remember it however you want to. This is iodine, and it is a molecule. MC will abbreviate that. Okay, so we have one more section left, and I hope I can keep from flipping back and forth on you. Sorry. So as we continue with this slide here, we have chlorine. Now, this one actually could be, I could be talking about a couple of different things. If it was an atom, it would be an element, but if it if we're specifically talking about chlorine as it occurs